So we're into the bonus material. Last time we were talking about the Schwarzschild space-time and black holes. And someone asked me, like, well, what's a geodesic, right? So if I write down, for example, a metric, let's take the Schwarzschild metric again. By the way, you'll notice that I'm giving you examples of metrics. I'm not defining what a metric is, right? And I think this is actually an easier way to understand what a metric is. But if you're wondering, hey, what is something, just ask me, okay? So the Schwarzschild spacetime, it's a variation of the Minkowski spacetime. It's minus, here, 1 minus m over 2r, 1 plus m over 2r squared to t squared, plus 1 plus m over 2r to the 4th. Now, by the way, you'll see other renditions or other coordinates for the Schwarzschild spacetime, and that's where they. This is where r equals the square root of x squared plus y squared plus z squared. Okay, so that's the Schwarzschild spacetime. Now, what does this mean, right? By the way, the other versions of the Schwarzschild spacetime metric, T will be the same, but they use a different notion of R. So I like this one because it's a conformal metric. You see how the x, y, and z's, they just get multiplied by a factor. The other one, you'll see it's more in spherical coordinates. And, you know, it's okay, but I like this more. I think this is actually easier to understand, especially for the first time. So what does this mean? It's really means the dot product is this, right? Okay, it means that if I have two vectors, let's say v and w, and v equals v, well, what does v equal? It equals v0, v1, v2, and v3, okay? Which we could also call vt, vx, vy, and vz. Now, it's traditional to use raised indices for vectors when you number them. I never have put the letters up there, but now that I think about it, I guess it makes sense if the numbers are up there. Why not put the letters up there? I don't know.
Early in the semester, you said that you would learn why Einstein's notation was good. Did we ever learn why it was good? You're like, just wait, we'll get there.
Yeah, I could do. Let's see, I could do a little diversion on that. It's the full story is a little bit lengthy, but basically, this is where I talk about vectors and covectors. Okay, but yeah, let's do it.
Okay.
Let's do it.
Sorry to derail.
No. It's actually a good question. So, what's the difference between a vector and a covector? You've probably heard the term covector before. Today's the day you get to learn like what it actually is. Okay. So, by the way, this vectors and covectors have nothing to do with. This doesn't rely on on a metric particularly, right? So just go back to R3. This is multivariable calculus we're doing here, okay? And so what is a vector? We already know what a vector is. I can have v equal v1 comma v2 comma v3. That's what a vector is. But let's be more precise. What this is v1 partial 1 plus v2 partial 2 plus v3 partial 3, okay? Which, by the way, we can even write with compact notation, summation over k of vk partial k. And then the Einstein summation notation, by the way, is, you don't even have to write the summation. You can just really say this equals vk partial k. And whenever you see a raised index and a lowered index, that means the summation symbol is implied. Saves chalk. Chalk's in short supply. Now, it makes things simpler to write, right? And so some of the calculations you do get really ridiculous where you got like, you might have 4 or 5 summation symbols. And it's like, it's kind of nice if I didn't have to write them down. And plus, whenever there's a raised index and a lowered index, you're always adding them up anyway. And so it just becomes implied, okay? Now, what is so right there, I could say that's an example of Einstein summation notation, right? But then you might say, but why are you raising some things and lowering other things? Well, you start to notice the patterns of which summations are always happening, and this is a way of checking that you actually should sum on them. Let me just point out what a covector is. That's a vector. What a covector is so by the way, the vectors, they have a basis, and that's partial 1, partial 2, partial 3. And by the way, you can also write that as d dx1, comma d dx2, comma d dx3. Now notice how we have lower indices for these. This is like I, j, and k, right? These are the unit vectors in the x, y, and z directions. Okay? And you're like, well, why are we thinking of them as partial derivatives? Well, what happens when you take the derivative along that vector? It's first order operator on functions, isn't it? So there's a one-to-one correspondence between vectors and directional derivatives in the direction of that vector. And then at some point you just realize vectors are directional derivatives, the things that take derivatives of functions. That's kind of their definition, actually. Okay. Which, by the way, is a very nice intrinsic notion of tangent vector, isn't it? Like, again, think of the potato, think of the tangent plane. What is that tangent plane? Well, if I have a third dimension, I can think what that tangent plane is in the third dimension, right? But if I define that tangent plane just to be the set of all first order, first order operators on functions, right, local, then there you go. Turns out that's what tangent vectors are. Okay, what's a covector? Well, this is D stuff. I've just been writing it like, what is D? What is dx defined to be? Dx, what you do is you put in a vector, and what it equals is the x coordinate of v. Definition, okay? More generally, if I take d, that would be like, or how about, that would, see, there's the whole thing. Do we number them, or how about we number them? So dxk would just give you vk. Is that maybe better? Okay. So that's what. So we have dx1, dx2, dx3, just like we have partial 1, partial 2, partial 3, and that's a definition. And so in general, dx1, dx2, dx3, right, form a basis for all linear mappings that take tangent vectors. So I'll just say tangent vectors. All right, in this here we could just say vectors, right? We're talking about vectors and covectors. Okay. So, take the space of all vectors into the real numbers. Okay. So, what are linear functionals on vectors? Well, that's an example of a linear functional on vectors. Right? Now, what does linear mean? It just means that if I take this v and multiply by 5, then the answer that comes out is 5 times as big, right? It also means if I put v plus w in there, then I get the answer for v plus the answer for w, right? So that'd be vk plus wk, and that's a linear mapping. It turns out that's all the possible. So once you say, hey, what are all possible linear mappings on that map vectors into the real numbers? Well, then that's what this dx1, dx2, and dx3 are. And notice that there's an interesting relationship here, and that is dxk of partial j, that this is going to equal 0 unless j equals k. And so this is actually a Dirac delta jk. So that equals 1 or 0. It's 1 if j equals k, and 0 otherwise. Okay? And okay, now you might say, well, why do I need to know about linear mappings from vectors to R? Well, I mean, this is math. I mean, why wouldn't you need to know about linear, right? You get what I'm saying? like we define everything. And it turns out, now here's one thing that's interesting though. Y'all see how the set of all possible vectors is a three-dimensional vector space in the example I've drawn, right? You have x, y, and z here, right? But then the set of all possible linear mappings is also a three-dimensional vector space, right? I'm not going to draw it, but I could, instead of I, J, and K, you have, instead of this being your basis, then you have this as your basis. Agreed? And so then I can say, oh, I have an idea. What is the space of all linear mappings of these guys into R? And it turns out it's just these guys. They're linear mappings on each other, right? So, for example, if I write down this identity here, right, I can also write this equivalently as, is this dxk sending partial j into the real numbers, or is it partial j sending dxk into the real numbers? I guess let me just define this, right? And so you see that the vectors are actually, they're also linear maps of the dxk's into the real numbers, just by flipping the definition of who's doing what to whom. Okay, so there's a duality here. Like if you play this game and say, okay, I have vectors. Okay, let's look at the space of all linear mappings of vectors into R. Oh, guess what? I get another three-dimensional space. Okay, let's look at the space of linear mappings of these guys into R. Yeah, you get another space, but so happens it's their first space you started with. Okay, so there's a duality here. And that's why there's called vectors and covectors. That's why there's no such thing as co-covectors. Like, why don't we just keep on going, right? So, we have vectors. Covectors are the set of linear mappings of vectors into R. Why don't we just do that trick again and get co-covectors? Well, it's because co-covectors are vectors. And so in particular, this allows us to understand what this Schwarzschild space-time metric is, because technically this is, these covectors are also known as one forms. So if you're wondering what a covector is, it's also a one form. You might say, why are there two different names? Well, it's because vectors and covectors are their own thing, but then there's also this thing called differential forms. It just so happens one forms are covectors, okay? But two forms have no relationship. It's a longer story. Let's not go there right now. And so, what is the dot product if I have some? And by the way, let's go. I kind of like, on the one hand, I like using x, y, and z and everything, right? But sometimes it's better to number things a little bit, right? I don't know. So when I'm writing vectors, I kind of like just to number them, okay? And so what this is saying, there's something kind of funny about when you write down the metric this way, is that this is notation. What this is really telling you is, it tells you exactly what sometimes people write this as ds squared, okay? It's the length of something squared. So in other words, if I want to know what the length of v squared is, all right? And really it should be written as plus or minus ds squared, because this could be negative, right? So you write it as, but no one ever does it. People write it as ds squared. So remember, the length of a vector squared in the case of special relativity is equal to, now if you're taking notes, you gotta leave some space here. Remember, it was negative v0 squared plus, and then leave some space there, v1 squared plus v2 squared plus v3 squared. Right, that was the Minkowski dot product. And what this is saying, and Minkowski space is that's one, and that's one. But now the length gets modified to just being this. Oops. Let's put those factors in. And now you can kind of see why this makes sense is because what we've evaluated there is you take plus or minus ds squared and then plug in the vector v, okay? Because if you plug in the vector v to dt, you're going to get the v0, right? So remember what this does, right? dxk of v just gives you that coordinate of the vector v. That's its definition. And so this gives you the time coordinate, this will give you v0, and then squared. And this dx of v is v1, and then dy of v is v2, and then dz, when you plug in v, gives you v3. And so, we're, this is an explicit formula, actually, when you understand what the definition of covectors are for plus or minus length v squared. Okay? And then it's understood that dot products are just go exactly the same way. So another way to understand this is saying that v dot product w, okay? Which, by the way, is sometimes written this way, sometimes it's written with the brackets. Let me see if I can squeeze them both in there. So v dot w is what you have in your textbook right now, but it's more common in graduate level text to write it this way. By the way, it's not to be confused with the V bracket, which is square brackets. This is angle brackets. And then what this equals in is minus this thing squared V0 W0 plus that to the fourth power times V1 W1 plus V2 W2 plus V3 W3. And so it's understood, like just do the dot product such that when V equals W, you get that. Okay, so technically it's we're giving you a length form, where it's the length squared of a vector. But it's also giving, from that, there's only one way to come up with a symmetric dot product, which when V equals W gives you that. Okay. Yes?
I think you miswrote the W vector.
Probably. Where?
When you define what W is.
Oh, thank you. Thank you. Other questions, comments, corrections? Okay, so, is notation perfect? No, but it's actually pretty good here. I think this is actually a pretty decent notation. Pretty decent. You guys see why? Pretty decent. It's just giving you an expression for plus or minus ds squared. Or, ds, you think of that as the length, right? So in other words, ds is the thing you would integrate if you're going to compute the length of a whirlwind. Like how much time did I experience? Well, integrate ds. It's the integral of ds, right? It's length in the usual sense. Okay, so that's the Schwarzschild metric. That's what metrics are. And we had a picture for the Schwarzschild metric. And this is where everything is one dimension higher that is drawn, right? And so this might be t equals 0, this is t equals minus 1, t equals plus 1. And so, we have the t-axis going up here, that's t, and then we have, the x. I guess that should be it. We have, actually I like to put x here and then y and z here. Okay. And then what happens here especially is this where, this, by the way, this is a sphere, it's an S2. Everything is one dimension higher than drawn. These are R3s, right? So each instant in time is a three-dimensional space. The set of unit vectors, and that R3 is an S2, right? But I can't, I can't draw in 4 dimensions. Can't even technically draw in 3 dimensions, right? But I can do a projection of 3 dimensions onto the 2-dimensional chalkboard, right? So we can sort of visualize things in 3 dimensions, right? But it's 4-dimensional, right? But close enough. I think that actually evokes the right picture pretty well, right? And so then I talked about gravity is just, you look at geodesics curve. Turns out they curve towards there. And they curve, the further away you are, the less they curve, the straighter they are. And then the closer you are, the more they curve. And so you have a force of gravity that's getting stronger as you get closer to the central region. And it turns out it's a 1 over distance squared force of gravity. So by the way, this is the thing where Einstein jumped up and down is when he solved the Einstein equation. You say, you figure out this curvature tensor equals 8 pi t. He had a different curvature tensor at first, the Ricci curvature, but anyway, curvature equals matter density. This is a 4 by 4 matrix at each point, so it's that. You set that equal to 0, and then you solve it for spherically symmetric solutions. And it turns out even the wrong curvature tensor still gives you the right answer here. So he got lucky with his first sort of not quite right equation. And he solved for this Schwarzschild space-time approximation. Actually, he didn't even solve it exactly. He just came up with an approximation of it. And what he realized was that not only did this give you a 1 over distance squared force of gravity, approximately, that it's not exactly a 1 over distance squared force of gravity. You get something that's a little bit different. As the distances get really close, it's not quite 1 over distance squared anymore. And then he's like, well, wait a second. Isn't it true that since 1859 they realized the orbit of Mercury is not exactly doing what Newton said? And then he checked, and sure enough, this explains the orbit of Mercury as accurately as can be measured. Right? So forget everything about Newtonian physics. That's wrong. That's a nice approximation. But, I mean, it's wrong. I mean, it's like, it's not complete. I mean, it's a good approximation. It gets the orbit of Mercury pretty well. It's just like heuristic. It's wrong. Okay, there's just no question about it. Like within, I don't know. Someone could look this up. Within how many standard deviations? Within 150 standard deviations. I don't know. Like 1,000 standard. And the point is, it's wrong, right? And it's kind of amazing they can measure things so accurately, because let me tell you what we're talking about. We're not talking about the orbit. It's not like Mercury is way off, right? But we're talking about, really talking about the elliptical orbit of Mercury, and it precesses, meaning the major axis of the ellipse changes every time it goes around once. And there's a rate at which that orbit precesses. And Newtonian physics and general relativity give different predictions for the rate of that precession. And the difference is like a 1% difference. Okay, it's really small. But they can measure that precession clear as day. And Newtonian physics is wrong. And general relativity gets as accurately as can be measured. So that's therefore our best theory of gravity today according to the data. Doesn't mean general relativity is right, by the way. It just means it's our best theory according to the data, right? So far it works out really, really well, right? Now, other good data for general relativity is this gravitational wave stuff. You may have heard of it in the news in the last 5 years especially. Or when did they do it? What year did they do the gravitational wave detection? 2015, 16?
Yeah.
Okay. And they've already awarded the Nobel Prizes. That's how quick, like normally it takes a while. You gotta make sure this is right? What year?
It was late 15, early 16.
Okay. And just to recap how ridiculous that is, I just want to, we should savor this. Because like every once in a while, like this is like G equals pi t is very natural from a pure mathematics standpoint. Like if you really appreciate geometry and you're like, hey, what would be the coolest geometric theory of the universe you could come up with, right? I mean, this is extremely natural. So the gravitational waves. So astronomers, if you look out into the sky, you see galaxies and stars first of all, right? And then also you see galaxies, right? But you'll notice that stars in the Milky Way system quite often are binary stars. It's not unusual to see binary stars. And apparently they form together, by the way. Look into that. It's pretty cool, actually. If you look into star formation, how they originally formed, it's not like two stars are just going through outer space and then all of a sudden they get gravitationally trapped by each other, right? What happens is they actually, the cloud of gas and dust that forms the stars, sometimes it forms two stars, right? And, that's pretty cool. And now, why is that? That's a pretty interesting question. I don't think I fully understand. I think if I had to guess, it's because the two-body problem is something kind of special. If you have two bodies orbiting each other, they will orbit in roughly elliptical orbits. It's stable. It's stable. The three-body problem is not stable. And but the two-body thing is stable. And so I suppose you get, as your matter is collapsing, sometimes you just get one star, but if it has some asymmetries, you get a little more density here and a little more density there. The collapse can happen on those two things, and it doesn't get all mixed up, right? It's reasonably stable, so why not? And you get two stars orbiting each other. But then Einstein's theory of general relativity predicts that and this is where physics gets rather complicated, because why isn't our sun a black hole? Why isn't all the mass collapsed into a black hole? Well, there's a lot of forces pushing back, right? The gravity is pushing the sun together, but then the other physical forces are pushing back. Okay, and the physics of stars, I think, is decently complicated, but apparently pretty well understood. So some of y'all are physicists, so you can explain it to me. But at some point, if the gravity gets strong enough, it just wins, and you get a black hole. And that's reasonably well understood. And in fact, the first bit of data was you look out into the universe, and for some reason you don't see any stars that are more than 10 solar masses, or there's some cutoff. It's oh, that's weird. The stars just don't ever want to have more than 10 solar masses of mass. What's going on, right? Why don't I see a 100 solar mass star? And then you figure, oh, it must be the cutoff for where black holes form, and I just can't see it, right? And so that's the first thing you're thinking. But then you realize that stars sometimes form binary systems. So wait a second, aren't there going to be situations where there's enough mass and you get binary black holes? And I'm yeah, it should happen. It should happen quite a bit. And how often? Well, look at the regular stars. How often does that happen? And you get some approximations. And so then you figure, oh, it must be these binary. Not only binary stars, but binary neutron stars and binary black holes. And I suppose, is there any reason why you couldn't have a regular star in a black hole? I suppose that would be possible, but it might be a little bit unusual, right? Because wouldn't you think that if either they both had a lot of mass, or they'd probably be roughly equal mass, I would think, right? But I suppose it's possible, and a neutron star in a black hole, I suppose it's possible. By the way, when you have binary neutron stars, this is where it's almost, these are super, super dense, right? And it's almost a black hole, but not quite. Then when they collide, right? So one thing about these orbits is that they decay. So unlike Newtonian physics, the binary systems go on forever in Newtonian physics. But in general relativity, there's energy loss each time. They're actually radiating gravitational waves. And so this was understood for a long time. And so that means the orbits are actually decaying. We're gradually spiraling into the sun. Hate to break it to you. I think on a time scale that's ridiculous, though. It's not. It's the least of our problems. All right. But anyway, when neutron stars decay and run into each other, that's pretty cataclysmic, by the way. And you can look that up, and apparently that is responsible for forming many of the higher elements on the periodic table. So you have both supernova explosions and binary neutron collisions. Neutron star collisions, I think, give us the periodic table of elements. So it's actually, where does almost every atom in this room come from? Is something rather spectacular. Right? If it's not hydrogen, helium, or lithium, think about it, which is practically everything. So practically this entire room, right? If it's not hydrogen, helium, or lithium, right? Then each of those atoms came from either a supernova explosion or a binary neutron star collision. I think those are the two leading things. And you can Google it and look up and see if they have other sources of these things too. But the point is something rather remarkable. Isn't that crazy? Right? And then, but then you have these explosions, and this stuff goes spraying out into outer space, and then the next thing you know, it collapses to form more stars, and some of it doesn't fall into the star by luck, and then next thing you know, it's the Earth, right? So it's crazy, actually. I mean, almost too hard to believe. Right? It's a crazy story. So, yeah, but the gravitational waves, when you have black holes that merge, and it's predicted on a certain frequency, then a huge amount of gravitational, they can simulate this on computers, right? Just solving g equals 0. And when they solve it on computers, they see a huge amount of gravitational waves emitted. Now, where are gravitational waves? They're just ripples in space-time. They're actually vacuum. There's no matter density. But it turns out that you can have the Einstein curvature tensor equal to 0, which are not vacuum. One example is Schwarzschild. Schwarzschild has g equals 0, but it's obviously not flat. It's got something there. It's a black hole, right? in this case, it's plane waves, or it's, it comes out, gravitational waves, the easiest way to solve them are plane waves. So, you can imagine some sort of explosion. Gravitational radiation is not even in every direction. But, as you get further and further out, it's pretty well approximated by a plane wave. And so you can see the plane wave solutions for gravitational waves derived in every GR textbook. And they've detected those gravitational waves passing through the Earth. Now, what's crazy about this is that those gravitational waves came from two black holes merging, orbiting around each other. The orbit decays, and boom, and it makes one black hole, right? And that when one black hole forms from two, that's like taking a rock and you throw it into the middle of a lake, and then boom, there's a big splash, and the waves go out, right? And so then we see those waves. We have a little rubber ducky, sitting, a long way away from the splash, and the rubber ducky goes like that, and then we see it. Actually, it goes like this with a certain characteristic pattern. Like, it's not just one blip. It's a certain characteristic waveform that they predicted in advance and then measured, right? We're like, wait a second, that's a gravitational wave from a binary black hole merger. Yes?
So, I know you said that gravity is like a result of the impression that like a massive object has in the universe.
Mm-hmm.
So, when you're talking about the waves, are you saying that we can measure them like as they just emanate or like go out forever? Or is it like a constant push down of that massive object?
No, it's a ripple, just like the rock in the pond. It's a temporary thing that lasts for just an instant, right?
Okay.
So, because what happens is, again, it's like throw the rock in the pond, right, and then the ripples go out. But if you're a rubber ducky, it's going to go like this just for a second as that splash passes through, right? But there was only one splash, right? And it's going at a characteristic speed. In case of two black holes merging, gravitational waves go at the speed of light.
Okay.
And so you have this ripple in space-time going at the speed of light, and it lasts just for a second as it passes through the Earth.
So how do we know where those ripples are when we try to measure them? Or is it just like a constant?
So you're asking, how do we know where that ripple came from?
Yes.
Okay, well, if this is the Earth, and you have a detector here, here, and here, let's say it's a two-dimensional Earth, right? And let's say that the source is here, right? So here comes the wave, right? It's going to hit the first one before it hits the first two, right? And so, if you have enough points on the Earth, you can figure out their relative distance to the source. And then you can say, oh, it must have come from over there. And then for the longest time, they never did make a visual connection with the gravitational wave source. But after a while, they got ready, and they're like, okay, next time you see a gravitational wave, tell me, and I'm going to turn my telescope. And someone said, oh, we see one. And they turned their telescope, boom, then they saw something, right? And so there was actually light coming from the black hole merger as well, right? Because, who knows what? There might have been some regular matter, so the black holes themselves aren't going to be anything, but there's regular matter in the vicinity, and then the black holes merge, and then that matter gets, accelerated, right? Accelerating matter radiates, and then you can maybe see something. So, yeah, so they've actually had visual confirmation of these black hole mergers as well. Yeah, so it's pretty crazy, okay? It's pretty crazy.
I think the detection, like the
Yeah.
interferometry
Yep.
they used to detect also gives you like a distance because it's like the two legs of an L. So if like this one shortens, then they know it's going that one shortened.
Oh, okay, all right. So you're telling me each of these detectors has a general notion of direction where it came from.
Yeah, because I think LIGO was two major detectors. So like they were able to figure out detection of 2 points or direction.
Well, they have two. One in Washington State and one in Louisiana or something like that.
That sounds right.
Okay,
They were,
something like that.
Very distant.
Yeah. So right there, it's going to give you some information, right? So,
Yeah.
and then I think they have one in Japan as well, perhaps.
Yeah,
And so-
it's not like they had like 12. They
Yeah.
had like 2 or 3.
Yeah.
I think the device itself gives some information.
And even the device itself, yeah. Okay, that sounds right. So, I'm very impressed with experimentalists, by the way. Let me just say for the record. These people are a different breed for me, okay? Like, the amount of patience required. I mean, they worked on this gravitational wave detector thing for decades before they made the first detection. People are getting, people are getting old doing this, right? And then,
Yeah, and they turned around and they immediately said we could get so much better results if we put the next one in space.
yeah.
If we just put it, so like
That's called VISA, right?
Yeah, they're gonna, yeah, so.
Are the plans on, are they actually doing it? Does it look like they're
I
doing it?
don't know how real or what time, I'm sure they'll do it at some point, I
Yeah.
don't know what the timeline is.
Yeah.
But that'd be super cool, because it would be made up of, each detector would be 3 satellites orbiting together
Mhm.
at like exact distances. So like if they ever
Right.
got closer together, we would know it's because of gravitational waves.
Perfect. No, it sounds good.
It
Sounds
got
good.
adopted by the European Space Agency.
So they're working on it.
Yeah, this year.
Cool. And so it's gonna happen, good.
How
Other,
do
yeah.
they get funding for decades on something that they,
National Science Foundation, European, what's it, European Space Agency or whatever it's called? I mean,
they
My
have
hard-earned
proof that
tax
it
dollars.
existed before they detected?
no, it's like, they could have spent billions of dollars and then nothing. I mean, that would have been possible. It's actually,
It's like fusion energy.
yeah, well, but see, with fusion research, there's a reward at the end of it. You get
Oh,
like
true.
free energy forever. In the case of gravitational waves, you're just like, oh, that's cool, right? Like, it's not exactly clear, like, how does this help humanity, right?
Sure, we'll turn it into a missile at some point or something.
Well, I think there is value. I mean, this in general, scientific exploration has value to society. Unfortunately, do you guys mind if I'm gonna give you a random topic of the day?
That's
Alright,
right.
yeah,
That's fine.
You guys like it, right?
yeah, sure.
Oppenheimer, the movie.
The movie.
Mm.
I mean, I haven't seen the movie yet, but when you think about, I'm sure it's good. Good? Should I see it?
Yeah.
Yeah, yeah,
It's,
you
it's
should.
long.
It's
I'm
pretty
gonna
good.
give you that preface.
Okay.
It's a long movie.
But I was watching another video on another topic. Everyone's talking about nuclear war and nuclear annihilation now, right? And oh my God, can we please? I just want to. This is like this would be so horrific. It's like we're not scared enough. I don't think we're scared enough. We don't talk about this enough. The world can end in an instant by human causes. We don't talk. I don't think we talk about this enough. I think we become complacent. I just want to point something out. If you have a 1% chance of the world coming to an end every year, then you've got 100 years. Do you guys get what I'm saying? If you have a 1 chance in 1,000 every year, then the world comes to an end in 1,000 years. All of this is unacceptable. This is horrifically horrible. Do you get where I'm coming from? Now, if you have 1 chance in 100 this year, and then 1 chance in 200 the next year, and 1 chance in 400 the year after that, you make it a geometric sequence, right?
Oh my gosh.
That adds up to something finite. Now that might be, okay, that's way better. Do we agree?
Sure, it's true.
So we need to make the odds of dying from nuclear annihilation a geometric series.
It needs to be strictly less than 1 over x.
It needs to pass the R test, or whatever they call it. Yeah, the ratio test. Actually, I think that's something that should be like golly, that should be a foreign. Shouldn't that be like a #1 foreign policy goal? Like if we what are we doing here? The world's going to come to an end. I mean, and I don't think, by the way, this is, you know what I think it is? I think maybe everyone says the world's coming to an end for every reason under the sun, and so we become sort of, used to the idea that when people say the world's coming to an end, they're exaggerating. Oh, yeah, whatever, it's a bunch of nonsense. Yeah, who says, oh, yeah, you say the world's coming to an end. No, this is real, okay? I think this is real. You prove me wrong, right? That if we had a full exchange nuclear attack, right? That the world as we know it, billions of people, well, I think it's tens to hundreds of millions of people would die instantly, and then billions of people would die in the next coming months as they starve to death because of the nuclear winter. Because food production worldwide goes down by a factor of 100, right? And there isn't enough food for everybody. Am I right? I mean, I like to be wrong. Please prove me wrong. But this is is science a net positive? I mean, we're all studying math and science. We like math and science, right? If we have a nuclear full exchange, then science was a net negative, wasn't it? And we would have just been better off if we had just sort of stuck to, maybe we draw a line somewhere and say, there's certain types of science that you're better off not knowing, right? And all of a sudden, what's that?
I mean, the Amish did that.
Yeah, the Amish were right. The Amish, we're about to prove the Amish right.
I'm in the middle. It's really good.
Right here. I don't know, they have it actually here. I
Yeah,
don't know what their year is.
that's very interesting. So let's not prove the Amish right. No offense to the Amish or any other. All right. Okay, that's my rant.
There's a lot of good quotes.
Oh, you're great. No, be careful how you quote me.
I just wrote that we need to make the chances of the world ending from nuclear weapons a geometric sequence that passes the art test.
There you go. You can quote me on that. How about that? That's fine. But or quote yourself. Actually, you know what? Let me just. I'll make another real quick point. When I make random comments like that, I probably haven't thought about them super carefully. I think this is true, but I'd like you to prove me wrong. Actually, I would really love that. But it's food for you to think about things and come up with your own ideas. And the last thing I'd ever want you to do is to believe some random thing just because I said it. Okay? I throw out an idea. You think about it. Do I agree? Do I disagree? Come to your own opinions. Make your own quotes. Okay. All right. So getting back to the good science here. Gravitational waves, I think, probably will not end in a nuclear winter. But in general, making scientific advancements is usually a good thing, right? In general, there's a lot of examples where that's been a very good thing. But then when I draw these curves, I'm saying, well, what are these curves? They're geodesics, right? And so then you're like, oh, what is a geodesic? And then I said, oh, it's this equation here. What you do is you take a curve, beta of s. You look at its derivative, and call that beta prime of s, which we, by the way, could call a capital T for the tangent vector, right? And so we say, look, it's a curve where the covariant derivative in the direction of t in the direction of t equals 0. All right, that's the geodesic equation. Okay, it says that, in other words, as I take the covariant derivative of, I could also write it as the covariant derivative of beta prime of s in the direction of beta prime of s is equal to 0. Okay? But then you're like, what is that again? Because remember how we defined it. We didn't have an intrinsic definition of covariant derivative. We didn't. And so I promised I would show you today what the covariant derivative actually is. Now what I also haven't done is I haven't told you what the Einstein curvature tensor is. So even saying g equals 0, well, what's that? But before you can understand curvature in its full glory, you have to understand what is the covariant derivative of a vector field in the direction of another vector field. That's obviously more basic, right? Okay. So now I'm about to tell you. And it's wild, it's crazy, it's non-trivial, okay? Not particularly intuitive, by the way. And in fact, it's a multivariable calculus problem. You could have, I'm about to show you something, and you could have done this in your multivariable calculus class. I wish they would. It's not realistic, because students would object. They'd be like, why are you showing me all this unnecessary stuff? Right? But this technically, what I'm about to show you, is multivariable calculus. So don't be intimidated. It is just Math 221, 219, or 222. Okay. So I have to point out some properties of the covariant derivative. So below this line here is multivariable calculus. Okay? Multivariable calculus. Starting here. Okay? So there's two properties that the covariant derivative has in multivariable calculus. One is called metric compatibility. But really it's just the dot product. Okay, so in other words, we have a metric, okay, in general, right? I mean, it could be some weird metric, but let's just pretend like we don't know about all the different metrics there are, right? We just use the metric from the usual dot product metric in multivariable calculus, right? Usual notions of length. Then what we want then is, but by the way, I'm going to start using dot products like this, okay? Do y'all mind if I, instead of writing this, I write that? Okay? And so if you take the dot product of two vectors, if you have three vector fields, so by the way, what we're going to do is we're going to have x, y, and z are vector fields. What is a vector field? It's not a vector, it's a vector at every point. They're at every point of your for any value of x, y, and z, right? In some region anyway. That's a vector field, right? So that might be a vector field x. Okay, now should I, it's actually kind of standard to use x, y, and z and u, v, and w as vector fields. I'm a little concerned about that because x is like a coordinate. So let me. I'm going to try not to use x, y, and z, even though that's kind of standard. I'll use. How about we call it the vector field v for vector field, right? And then what we're going to do is we'll let u, v, and w be vector fields. Okay. Maybe that'll be less confusing. Okay. All right. Symmetric compatibility says if I have a vector field y and z, and I take their dot product. Vector field, dot product of vector field equals a number at each point, which otherwise known as a function. You agreed? Okay. Now I want to, I'll use y and z again, sorry. I'm trying to use v and w, okay. V and w, okay. So vector field, dot product at each point is a number at each point, otherwise known as a function, right? Functions, we can take directional derivatives. So we'll take u and take the directional derivative in the direction of v and w. What do we get? Well, product rule, right? We get this. Do y'all recognize the product rule? Weird notation, admittedly. This means directional derivative. Y'all remember that, right? You put a function in there, okay? So notation is hard to get used to, but it just says the directional derivative of this dot product. You can think about it in your old notation if you want. It just means the derivative of the first thing times the second thing plus first thing times derivative of the second thing. Everybody agree? Any questions, comments? That's the product rule. So really it's the product rule. Okay? Now, what is this metric here? Well, just think of it as the usual metric from multivariable calculus, right? In other words, V1, the usual dot product. Now later on, we're going to change it to this, so some arbitrary metrics, correct? But for now, just think of it as the usual. That's totally fine. Okay, so if we're going to come up with a definition, we're going to come up with a definition of what this thing does. How does it work? What is this equal here? Equals what, right? We're trying to define, give me a vector, given two vector fields, what's the derivative of one vector field in the direction of the other? Well, how about this? I want it to have this property called metric compatibility. Fair enough, so that way we can still have a product rule. All in favor? Yeah. Make life simple on us, right? Let's try to figure out the rules that were true before and try and keep them, right? Seems reasonable. Okay. Now you might say, is there only one, would it be nice if there was only one way to define this such that that was true? Wouldn't that be nice? And then we'd be home free, boom, done. But unfortunately, it's not the case. There's another rule we have to use, it's called torsion free. Okay. Now, this requires me to come up with a new thing. I got to tell you what it is. It's called the Lie bracket of two vector fields. That is another vector field. Okay, so let me in fact name it. The Lie bracket of two vector fields. Let's call the vector fields v and w. Is another vector field u such that for all smooth functions, the following thing is true. You ready? If you take a function f, okay? If I take its directional derivative with a vector field, that gives me another function, right? At each point, it's a number, but the point is it's a number at every point, so therefore that's called a function, right? So w of f is in fact a function, right? Function, vector field, w of f is a function. So now I can take its directional derivative in the direction of v. Directional derivative of a function is another function. So this is a function. This function has second order derivatives in f. Agreed? Okay. Well, there's another way to compute the sort of the second derivative of f given two vector fields, which is I could put w first and then v on the inside, right? So this is two different ways to compute a second derivative of f given two vector fields. Guess what? They're not in general the same. It turns out these types of derivatives don't commute. These are not partial derivatives. These are directional derivatives. Okay? Partial derivatives commute. Doesn't matter the order, right? X, y partial derivatives commute. And so, and by the way, if v and w were like the vector fields I, j, and k, right? Like coordinate vector fields, then actually they would commute. But these aren't. These are arbitrary vector fields. These things don't commute. However, here's what's interesting. The second order part, the second derivatives of f, of whether it be this and this, actually are the same. These things are the same except for the first derivative. So if you take the derivative of w applied to f, when you take this derivative, you got the derivatives on w, but you also get second order derivatives on f. But in particular, when you take the derivative, some of this is going to be derivatives on w, and you only get first order derivatives on f. So anyway, if you look at the difference, turns out all the second derivatives of f cancel. Okay? So the first, and this is a calculation which I won't do. I'll leave it as an exercise for you guys. It's a standard exercise. That this minus that is in fact a first derivative of f. It's a first order operator. What I've written down there is a first order operator on f. There are no second derivatives. They cancel. Had I made that a plus sign, that wouldn't be true. Okay? Everybody understand? This is only first derivatives of f are left. Well, guess what? Remember when we said first order operators are in one-to-one correspondence with vector fields? So this, in other words, this corresponds to some vector. So we say, okay, well, what do you want to call that vector? How about u? That's what the Lie bracket of v and w is. It's the first order operator u that you get when you subtract off the two second order derivatives. And then what we say is we say that u is equal to the Lie bracket of v and f. This is the Lie bracket. Notice it's not an angle bracket. It's not the same as the angle bracket here. This is like a rectangle bracket or whatever. A square bracket, box bracket.
Has no relation to the commutator.
Well, it's a commutator of sorts, right?
Yeah.
I mean, if this were 0, then these would commute. So yeah, it's inspired by the same concept. Yeah. Okay. Now, why is it? Let me tell you why you never heard about the Lie bracket in multivariable calculus, even though that's clearly a multivariable calculus concept. Can we agree? This does not require anything about metrics or anything. I never said anything about a metric. That's just talking about directional derivatives and whether or not they commute, right? And the answer is no, and generally they don't. And what the difference is, though, is another vector field. Okay, so clearly you could have learned that in 219. Let me tell you why you never discuss it in 219. Because there's an identity. Okay, and that identity is that if you take the Lie bracket of v and w, there's a formula for it, and it just equals that. Okay, so if this ever came up in one of your homework problems in multivariable calculus, you would have just computed, and there's no reason to have a new name for this. It just equals that. It turns out it equals the difference of these two things. Okay? And so you sort of were unaware that this was going on all the time. Okay? But it's nevertheless true. And I'll leave that as an exercise. It's a multivariable calculus exercise for you. And that's what torsion free is. We want to maintain this property. Now, here's the deep thing. The key thing to understand is that this actually is a property of this connection thing, this upside down triangle. Right? Because see, this is still well defined. Directional derivatives are things we understand. That makes sense to the ant. When we're talking about intrinsic geometry, the ant understands directional derivatives, so the ant understands Lie brackets. You try to explain the Lie bracket to a mathematician ant, he's like, duh. No. That's just multivariable calculus. I know what the Lie bracket is. Everybody knows what the Lie bracket is. But you try to talk about covariant derivatives, then it's like, and use your definition about the third dimension. He's like, third dimension what? Right? Okay. So now we see, so now wouldn't it be neat? Wouldn't it be neat if there was a unique connection, a unique way of defining this so that these two properties were true? Right? Guess what? There is. The only one, exactly one. That's the theorem. That when you say, I want to keep the properties that I always had before, then there's only one way to do it. Pretty cool? Okay. Now, let me see here. To do this, what I'm going to do, I'm going to modify this property here. I'm going to point out that if I can then take a dot product with any u here, okay? And then I'm going to take a dot product with u here, and then a dot product. Well, actually, I don't want to mess it up, but that's how we're going to be using. I'm just going to leave it like this, I guess. But that's how we're going to be using. We're going to be taking dot products with u's. But I think we can just leave it like this. Okay. All right. So now I'm in a little bit of a rush. So let me see if I can get this. So what we want is, I'm about to give you an example of why patience is also required for mathematicians. Not 20 years of patience like the physicists to detect gravitational waves, but nevertheless patience. Because let's say I want to compute a formula for this. Oh, I look at it and I say, oh, look at that. I see that. That's exactly what I want right there, right? Okay. So what I do is I say, oh, okay, I see what this is. This is, there's so many different ways we could do this. Okay, do it this way. Okay, fine. That equals u. You guys are going to have to help me here, okay? And then minus this thing. I'm thinking about presentation right now. Let me do it a different way. I think it's going to be better. Sorry. Let's just write down the first identity. I think this would be the best way to present it. So we get u of, in fact, let me make a list here. Good terms. And so what's a good term is u of v dot product w. See, we know what this is. This is just, we're given a metric. So think of it as someone gives you a metric and you want to figure out what the geodesics are, so you want to know what the connection is. Okay, so you know the metric, you know directional derivatives. So this is a good term. I know what that is. And so then this equals the thing I'm trying to solve for. And now if it just equaled this, if we just had the one term here, then we'd be done. I'd be like, oh, okay, we're done. I can just define this to be that. But there's not just that. It's this other term here. So we get the bad terms over here. Okay? So, we get a bad term here. It's like, what can we do to get rid of this term? And then we look at the second identity, and we're like, there's a minus sign here. Could we maybe use this identity here somehow? Wouldn't it be neat if I could have a minus v uw? That would be nice. Okay, how could I do that? Well, you guys see what I did? This right here is a Lie bracket, right? And so this is equal to v, Lie bracket, w, and u. This is where you better check me. If I get off by a sign or anything, it's going to mess everything up. Okay, so what we did is, this is the term we're trying to solve for. Okay, these are the good terms. We know what they are. The Lie bracket, w bracket u, is just this minus that, and that dot product did everything with v. And now, look at this. Those terms cancel. If I were to add up these two equations, those terms cancel. And we'd be done, except, dagnabbit, I still got this one bad term over here. Right? I mean, this is just a directional derivative of a dot product that we're given. That's a Lie bracket. Remember, Lie brackets are just, the ant understands that. That's just directional derivatives, right? And dot product, sure we got that. So, we just have this other bad term here. How can we get rid of it? then you go back to your first identity and say, oh, wait a second, I recognize that. Isn't that just sort of like this term here? Okay, yeah, it sort of is, right? And so this right here is sort of like, I'll put a minus sign here. I want to cancel that term out, right? And then minus, so this would be the product rule, so you guys better check me here. So this is going to be negative W VU. Right? And then use the product rule. You take, it says minus VU, they got the W derivative here, W derivative there. And now, these two terms, when you add, if we were to add up all these equations, they cancel. Right? But we're like, Dad, now we got another bad term to get rid of. Right? And this is where a lot of people would give up. But a select few people persist. And they say, is there a way to get rid of that term? And I think, well, let's go back to this other identity. Leave bracket term here. Okay. Let's see what we got here. What I want is I want a plus W V U here, right? Okay, if I'm making a leave bracket, then I would need a minus Did I do that right? So W leave bracket, so everything's dot product to U, and then leave bracket of W and V is this minus that. And now, these two terms cancel. Right? And so then your persistent people, but not sufficiently persistent people, would give up at this point. But suppose you keep going and say, okay, well, I use the leave bracket identity. Let's just keep going and see what happens here, right? Use this, I want to get rid of this term here using the metric compatibility argument. And so that means I need a plus this term. And so this would be the product rule one. And so that means I'm going to want a W, right? And now I have this W, U, and V. It's a directional derivative in the V direction of W dot U. Did I do it right? And now, okay, so you got the V derivative of this, and then the V derivative of the second thing, right? And now these two terms, they add up. Still got a bad term. I think we should give up.
Yeah.
But you guys say we've given it a good try. Probably we've written 5 equations. This is never going to work out, right? Or we could just do it. We try a little bit longer. How many times do you think we should try?
Once.
What, just one more?
Yes.
Why one more?
Because there are 3 variables and done in each.
There's 6 different ways to arrange 3 things, right? And so
Yeah.
you're thinking 3 factorial is 6, and okay, so your instincts were right on. Actually, do it one more time, and it's something.
Also, you set it up linguistically.
Yes, all right. Okay, fair enough, right? Especially okay. Coming down, I'm selling the quitting. Okay, don't quit. This lesson was ultimately a story about not quitting. Okay, now we have to kill this term off, and so we want a minus W V U here, and then so what is that? I want to use that, make it a leave bracket, and so that means this is going to be a W UV, right? And so then what we have here is W, and then the leave bracket of U and V equals this, right? And then you got this minus that, we take the whole thing, dot product. Now these two terms cancel. But we still have a term here we can't solve for, right? I thought it was going to work. You told me it would work after doing it 6 times.
It's just the same as the first thing.
It did work, you're right. This term and that term in the box there, they're equal. You add everything all up, right? And you get 6 terms here is equal to 2 variant derivative of V in the direction of U dot product W. And now you have a formula for this, and it's those sum of those 6 terms divided by 2. And touchdown, it works. Okay? And so the moral of the story, I guess, is try things at least 6 times. No. It could have been 12, it could have been 24, right? I mean, I think the real question is, will this come to a satisfactory end or not, right? And it turns out there was a trick. Yeah, if you come back to the thing I started with, by the way, sometimes when you do stuff like this, you get the same term, but if there was a minus there instead of a plus, then you would get 0, and then you get, well, at least then you would have an identity. These 6 things add up to 0, right? Okay, so, yeah, I would say persistence paid off here. Okay, this is a formula. We now have a formula. Here's the point. These 6 terms are all good terms. These things all make sense to the int. And you divide by 2, and that gives you a formula for the covariant derivative dot product w. But if you know a vector dot product any possible w, you know the vector, right? And so this gives you the formula for, this is called the Causual formula. This is known as the Levi-Civita connection. So this is called the Levi-Civita connection. And that's called the Causual formula here. Now, I know what you're thinking right now. You're like, okay, that's great. You proved that such a connection exists. Surely, you don't expect me to actually use this formula to compute covariant derivatives of vector fields. Yes, you do. I hate to break it to you. That is the formula that we all use. We actually use this Causual formula. So you thought it was so easy. Come on, how hard could it be? Directional derivatives are just kind of obvious, right? Very intuitive. But for some reason, when you take the derivative of a vector field in the direction of another vector field, I got to use this monstrosity. And the answer is yes. When you're doing intrinsic geometry, that's the only way to do it. That's why it's not. Like I told you, I remember I told you I'd be very impressed if anyone would come up with the stuff by themselves. Yeah, I don't know anyone who actually came up with that themselves. Like I learned that reading in a book. I guess Levi-Civita must have come up with it. Right? Or maybe Causual, I'm not really sure of the history exactly. Someone had to figure this out. But yeah, this formula, by the way, this formula gives you the same answer as what you were doing in R3 the whole time. It's just a way harder way of getting it. Right? So it has to, right? Okay, what have we not? I've not really done the complete proof. We basically, what do we show? We show that if you want to have these 2 properties, the metric compatibility and the torsion free, which you have in multivariable calculus for your connection there, then they would have this formula. Here's a formula for it. There's only one possibility, but we still haven't proved that this formula for a connection actually has these 2 properties even. But it turns out it does. Okay, so that's something to verify. You work out your formula. Okay, now that I have a formula for it, does this actually have these properties? In other words, does it go both ways? This implies that, but does this imply that? So there's something you can check, and sure enough, it does. It does have these properties. And sure enough, it gives and therefore, by the way, it's unique. And so I guess it has to give the same answer as the connection you were using before, right? But it's kind of far from obvious that this is going to give you the same answer, but it does. So, if you have a 3rd dimension, why wouldn't you use it, right? If you had a 3rd dimension, just take the coordinate derivatives like you were doing in multivariable calculus, and you got your connection that way, then project, right? But if you don't have a 3rd dimension, you can't do that, and therefore all you got is this. This is the only thing you got. Okay, and complicated formulas like this is why people like me have jobs, right? It's like geometry is actually kind of interesting, right? And then what we'll discuss next week is, okay, now that we know how to take derivatives of vector fields in the direction of other vector fields, guess what? Second derivatives of vector fields is where curvature shows up. Okay, and so we're going to define the Riemann curvature for tensor about a formula that has second derivatives of vector fields in directions of other vector fields. So now that we have this, we actually can define, we're off to the races now. And we can define what curvature is, and then then we'll actually know what this Einstein curvature is that gives you these beautiful metrics. Okay. All right, have a good weekend. See you guys next week. I think you'll have homework due Friday, right?
Yeah.
So, and then how many more of the traditional homework assignments do you have?
Just one.
One more after this.
This one plus one more?
Yeah.